a lot of the visualizations you'll be seeing are three-dimensional in nature. That's something that you can do in a headset that you can't do on a screen, and it has in the past been a little bit controversial. So about 10 years ago, actually, it was quite controversial. In a really great book that we use in teaching visualization quite a lot, and is used in many other places for teaching visualization. Visualization Analysis Design is a book by Tamara Munzner that was published in about 2015. And she spends about 14 pages demolishing the use of 3D graphics for data visualization, or at least what she calls unjustified use of 3D graphics. And she definitely had a point that static projections of 3D visualizations suffer from occlusions, perspective distortion, and awkward interaction if you're trying to use something like a mouse to interact with a 3D rotating volume, which is sort of where things were about 10 or so years ago, pre-headset. And this is some of that early work that that Kai mentioned. So this is 2005. This is the very end of my PhD, about the time I met Kai, and we worked together a little bit on some of these 3D systems. This is a study I did evaluating a kind of 3D visualization of what I was calling at the time 2.5D kind of time series curves. So this is inflation versus unemployment curves. And because of all the limitations of 2D screens, which is all we had at the time, I tried building a physicalization of this data set and did a study, not a very good study. I don't think it wasn't very well controlled as my first study, but it was really interesting, this exercise of creating a 3D physicalization of data and looking at what the pros and cons of allowing people to pick up data and experiment with it and interact with it directly were. So after that, as I said, data visualization in 3D was quite unpopular for a while. The end of my PhD work was probably the tail end of the first wave of 3D graphics popularity, which was triggered by really quite the emergence of the first performant 3D graphics cards in desktop PCs. But it kind of, after a while, it kind of died out in data visualization. People went strictly old school 2D. And then when I came back to Monash in about 2012, we were beneficiaries of a fortuitous kind of piece of equipment that arrived in a new building we had at the time. So this is a Cave 2 installation in one of our buildings in the on the Monash Clayton campus. And it's here showing a bunch of, I think it's fMRI data, so flows of neuron bundles. And this is a bunch of VIPs touring the cave. And in all honesty, that's probably the main use of that the Monash Cave 2 saw. A lot of VIP tours of this really quite impressive facility. So it had about 80 of these fairly high resolution screens and Vicon tracking systems. So those are infrared cameras all around the top. And but as I said, 3D visualization was very uncool at the time. So we did a lot of quite traditional 2D visualizations, just treating it as a big wall display. And next door to the K, we had another facility, which we called the Future Control Room, which is this one in the bottom right down here. And that at the time we saw as a more practical kind of visualization facility, where people could come together to collaborate on quite conventional 2D displays. However, shortly after that, around 2014, the first Oculus Rift the first Oculus Rift VR headsets arrived, and they triggered a wave of excitement amongst us, but many others as well, about the possibilities of truly immersive 3D visualization on low-cost devices. That Cave 2 facility I mentioned, that was about $2 million, and an Oculus Rift developer kit at the time was about $400 or $500. So much more affordable, and we saw as being potentially quite revolutionary in the kind of applications that it might open up. Thinking slightly longer term, we thought very strongly at the time that the future of visualization was not so much these expensive visualization centers like the Cave 2 or like our future control room, but something much more like this, where a bunch of people could sit around with headsets not much more awkward and cumbersome than the glasses we all have to wear anyway, or perhaps nothing at all. Maybe one day there'd be implants or contact lenses or something that would give people a similar capability. And then you'd be able to sit around and have 3D information graphics appear in the space around you and be able to interact with it on tabletops like this one, or floating around in the space. Why might that be compelling? Okay, so let me give you a little case study of an industrial scenario that has a very bad outcome because of inappropriate 2D data visualization.
Remember, short controlled bursts. 8 meters. 7. 6.
Can't be, that's inside the room.
It's reading right, man, look.
Well, you're not reading it right.
5 meters, man. 4. What the hell? Oh my God. Oh,
Give me the light.
So, okay, that's actually Aliens, the movie, which is a really, really good movie. And what happened there was they were using this 2D display device, which we've rendered in a little cartoon here. So they had a 2D display device capturing 3D positions of these aliens that were encroaching on their space, and before too long, they realized that the proximity sensor is correct, but the aliens are very close to them in the plane, but they're coming through the ceiling. And so, if only they'd had proper 3D visualization, they might have been able to see what was going on and react more effectively. Anyway, that was a bit of fun we had producing a chapter for a book on mobile data visualization a few years ago. And although it's a kind of fun scenario, if you don't mind the sort of space marine paramilitary kind of thing, it does make a point that you need visualizations that are accurate to the spatial nature of the data that they're trying to represent. Shortly after, or around the time we got our first Oculus Rift developers kits in 2014, we started publishing papers on this topic of immersive analytics, which is a theme that we started pushing quite hard, and we ran a lot of workshops at various places, including conferences like Viz, to try and promote people who were thinking about the ways that these emerging display technologies could be used, not just for visualizing 3D data, but as we've said here, to remove barriers between people, their data, and the tools they use for analysis. So there's something about embodiment there, and about how we intuit that it's somehow better if you can perceive information represented as objects that you can interact with in a natural way. To support data understanding and decision-making everywhere and by everyone. So the other piece of technology that was appearing at the same time as, or shortly after the Oculus Rift, was the HoloLens. The first Microsoft HoloLens 1 device came out around 2015, 2016. And that was a portable completely self-contained device that didn't do VR but AR, and has the potential to allow you to do immersive visualization anywhere in all sorts of contexts. So that was quite exciting. And the final thing here is that if you're going to have embodied visualizations that are embodied in the space around you, you need a new set of tools to interact with them. The standard mechanisms for interaction, like mice and keyboards, they don't cut it anymore. We've got to reinvent how we interact with information to make the best possible use of all sensory channels. So that's our little definition of immersive analytics. It's the use of engaging embodied analysis tools to support data understanding and decision making. All right, we had a book, came out around 2018, and sort of laid out the research agenda for this topic. Since then, we've been building a lot of immersive analytics systems, and we've learned a fair bit along the way. I'll talk about some of the things we've learned as we go. And where we are now in 2023, I remain very excited, even though the technologies haven't exploded quite as much as we might have expected. The headsets are still somewhat clunky. I think it's inevitable that they will become something more like the glasses that we wear every day. And at that time, we will be able to use visualization in all sorts of ways that we can't currently. And so as researchers, it's important that we understand not just the technology, but from the human side, what the different ways of interacting with these kind of immersive environments are that are effective for data visualization and sense making. So that's one grand challenge. Another possibility is to make data sense making available for a much wider audience, not just experts, but to allow people to come together, experts and novices or experts in different domains, and be able to talk together in a shared environment. And this final grand challenge that I put here is kind of a longer term vision about what the ultimate, so I'll talk about that a little bit more, what the ultimate kind of knowledge representation or visualization system, not just visualization, but multisensory knowledge representation system will be if you throw away all the limitations of technology and use all the resources you have to build the bestest, most immersive system you can. So I'll give you some examples of that as we go along as well. Okay, I think I'll cut through to the examples, or this is going to take a very long time. A quick note about some of the cognitive science that we're sort of grappling with, trying to understand how visualization can be made to allow people to really understand complex data. So this is a visualization of a large network, and quite a dense network. And there's a question about whether what the limits of network visualization are. As Kai mentioned at the start, network visualization is something I've done a lot of over the years. And early on, it was all about building algorithms to create pictures of the biggest, most complicated graphs we could. But at some point, you run up against limitations of even the best algorithms can't untangle a hairball like this. And there's a question about what you can actually see in a picture like this. So we did a study around 2019, 2020, where we tried to figure out what the limitations, what the scalability of network visualization from a cognitive load perspective was. And to do this, we put people in EEG headsets and had them complete shortest pathfinding tasks on a whole lot of quite dense graphs, and came up with a model of hardness of visualization related to various properties of a graph. And a very strong dimension in this hardness model is the density of the graph, and as well as the number of nodes, but especially the density. And what we found is that when you visualize visualize hard networks, or when you give people tasks to complete on hard networks, completely different parts of their brain light up, which the cognitive scientists that we worked with, the cognitive psychologists that we worked with, told us were related to different parts of the brain, related to short-term memory use, whereas the easy networks, the sparse networks, were more straightforward spatial navigation. So, so by the way, the cutoff point seemed to be about dense graphs with about 75 nodes. Is beyond that, it just gets too difficult. Okay, so instead of that, we came up with techniques other than network visualizations, node link diagrams, to visualize large complex networks, which tried to keep a cap on the complexity of the visualizations. And we also focused on producing really high quality visualizations of relatively small graphs. Anyway, let me skip past that and get back to the Cave 2, which is what I really wanted to talk about today. And immersive visualization. So around 2015, we were still trying to figure out what to do with this Cave 2. And we had our Oculus Rift developer kits that look quite clunky now, although actually they were lower resolution, but modern VR headsets are still quite similar. And we were interested in understanding basically which was better for collaborative network visualization. This $2 million Cave 2 or a Oculus Rift headset set up with 2 Oculus Rifts and a couple of PCs for a few $1,000s. And the results were quite interesting. So, and I can kind of sum them up with a couple of top-down visualizations of the pairs of people that were using this study. Once again, the tasks that they were completing were finding shortest paths between pairs of nodes in a graph, and the graph kind of wrapped around them, as you can see here, both in the cave, but also in the headset. And so if you look at their head movements top down as they completed these tasks, what you see is that the 2 people, so one person's green, the other person's purple, they moved about sort of fairly independently. And also their vertical head movements were quite independent. But when you contrast that with the Cave 2, the pair who were doing it in the Cave 2, we found that they moved together. And one person had a lot of vertical head movement, and the other person had a very static vertical head position. And the reason, well, it's actually kind of obvious. In the Cave 2, only one person has the correct perspective view of the visualization. You can get very fancy cave setups where you can multiplex the view and have shutter glasses so that both people can have the view, the correct perspective view, even as they move around independently. But we didn't have that. And to be honest, even such a setup is never going to scale to more than a couple of people. Whereas VR headsets, obviously everybody gets the correct view of the data. And that turns out to be very important in these kind of analysis scenarios. It really did lead to a difference in behavior and a difference in effectiveness in solving these visualization tasks that we gave people. So on the theme of studies looking at how people interact with data in immersive environments, another thing that we noticed was becoming ubiquitous, not only in Cave 2 kind of environments. You will have noticed that in that previous one we had the data visuals wrap around the person, and this is quite common, not just in Cave 2s where obviously you're surrounded on all sides by screens. But we've noticed in the various systems that we've built that people tend, when they arrange data visualization elements around them, they tend to do it at arm's length. So I'll show you some systems later on where people can construct data visualizations in immersive environments and place them wherever they like. And we notice this quite strongly. There could be a couple of reasons for this, why they would arrange visualizations in sort of circle around them. One is a lot of VR headsets are tethered, and so you don't feel particularly comfortable walking without tripping over the cable. Although newer headsets like the Oculus Quest don't have that problem. They're also also HoloLens. They're self-contained devices with no cable. But still, people perhaps are not as confident walking around in VR as they might be, and so in real life. And so they tend to stand still and just rotate to access information. So that led us to a research question, which was to see what the effects of different spatial layouts of information around people, how it would affect, especially spatial memory. So this is a study run by our student, Joe Liu, and presented earlier this year at the ISS conference in, I think it was Wellington. Okay, so he basically ran a memory study similar to spatial memory studies that have been done in psychology in the past, but he did it in VR, and we were testing either a wall display like this one, and so people had to remember patterns of white cards either on a flat wall display or in a circular configuration or in a semicircular configuration. And the research question was whether the different arrangements would affect their spatial memory. There's not that many people on the call. We could make this a little bit interactive. Maybe I can poll you. Who thinks you can either turn off your microphone and tell me directly or type something in the chat. Who thinks that that a wraparound, a circular layout will be better than a flat layout? That's right, circular, flat. I'll get you started. All right. So what I've done there is I've probably anchored your expectations by starting off with circle. Actually, it turned out that that the circle was absolutely atrocious. People were really exhausted and found it difficult, and it was really quite significant, the result that we got, that the wall display, the flat display, allowed people to remember these patterns much more effectively, which we found really interesting, given that these kind of circular arrangements of immersive data visualizations were becoming somewhat ubiquitous. So the result is please use circular displays with caution. The other thing I wanted to talk about, so that's kind of talking about some cognitive foundations of immersive analytics, and there's still loads and loads of research questions, loads of work to be done about how to exploring this design space of immersive visualization, and there's lots of people doing that around the world, not just us, and it's quite exciting. What I'm going to talk about now is another little theme that's been running through our work for a few years, which is this idea of spatio-data coordination, the idea that that the interaction spaces, the space of interaction with data, should somehow be should conform to the dimensionality of the data itself. Probably the easiest way to explain that is with some examples. So we made, this is also around 2016, 2017, we made some early prototype interaction devices, basically thinking that that the standard, this is a slightly newer iteration of Vive headset than the Oculus Rifts before. So I think, yeah, it was about 2016, 2017 that we were doing this. We were feeling that the standard VR controllers don't really offer you much support when you're interacting with 3D data for things like accurate, precise selection of volumes that are aligned with the dimensions of the data. So if you've got an X, Y, and a Z dimension that are mapped to different data dimensions, it may be better to have a device that allows you to very precisely select volumes within that space. And so these are a couple of different devices that we built to explore this notion. So one we called a cube mouse. So it was laptop touch sensors on 3 sides of a cube. And the other one was this 3D slider axis arrangement. So 6 sliders, the kind of sliders you find on mixing consoles. And we arrange them in 3 orthogonal axes, as you can see there. And I just realized how crazy out of order these slides are. Let me jump ahead. Maybe I'll show you this one. So, okay. Remember this design. At the time we published this first paper, we didn't really evaluate it, but we did that later. So we'll come back to that. This idea of a spatial data coordinated interaction space. Okay, so
flow maps.
This is a really fun space to figure out how you effectively use 3D visualization, the possibilities of 3D visualization effectively. And as Tamara Munzner obviously pointed out, and many others pointed out, if you're not visualizing truly 3-dimensional data, then your visualizations will suffer needlessly from things like occlusions. So this is my former student, Yilong Yang, who is now a great visualization researcher in his own right at Virginia Tech. And this is a system that Yilong built a few years ago, which we called TiltMap. The idea here is that it's a visualization that you can manipulate in 3D, and as you move it, as you tilt it, it changes form. So when you're looking at it directly from above, it's a choropleth map, and then when you tilt it, it turns into a prism map, and when it's fully horizontal to you, it becomes a bar chart, like as you see there. Let me play that. We've got questions appearing in the chat. I'll come back to those. Okay. So here's one of the examples of visualizations in rooms with people placing data around them. This is from another one of my former students, now at Stuttgart, Benjamin Lee. He built this really cool system, which we called Fiesta, which allowed people to, wearing these backpack PCs, which was the most portable VR system we could manage at the time. This is a few years ago now. They could interact 3 at a time to explore data in a kind of immersive room, and they were co-located in the same space. They saw each other's avatars, so they didn't walk into each other. And this was kind of Benjamin's best effort to build a fully fledged 3D analytics system in an immersive environment. Okay. Let me play this video. So Benjamin did a study with 10 groups of 3 participants in each group. And why is this video stopped playing? And he had 2 different conditions. So one was just visualizations placed on the walls, and You could create the other condition allowed you to create 3D visualizations and place them on a table in the center of the room. And across about an hour and a half of people exploring this data set, we had lots of findings. What we found that was really interesting was that this virtual table wasn't really very useful. People preferred to be able to place visualizations wherever they liked, and placing furniture in the room kind of just gets in their way. Okay. Another visualization system. This is coming back to the axis idea. We were inspired by that 3D axis device that we built to think, well, what if you could pick up the axes and place them in the room around you? And so we came up with this IMAXes idea, where the axis is the primary interaction affordance in the space. And so the idea is, if you have multi-dimensional data, there's a spreadsheet of multi-dimensional data. You can, typical ways to visualize high-dimensional data as a scatter plot or as parallel coordinates. I assume that people on the call are familiar with these visualization idioms, visual idioms. And we used the idea of the axis as the primary embodied affordance for interaction. And here's the system we built. So it starts off with a shelf of the data dimensions on the wall of the room like this. And you can pick up the axes and clone them and drag them into the room and create either parallel coordinate plots or scatter plots, depending on how you hold the axes relative to each other. And I'm going to skip ahead because we did a lot of stuff with this concept, including a kind of longitudinal study with economists, looking at how they would use this IMAXes system to analyze their own data. And this is one of the places where we saw this pattern of people tending to arrange visualizations in a circle around them. And then we came back to this beta axis, or this slider physical axis idea. So although the VR system was really nice, we were still kind of captured by the idea of being able to do this in augmented reality with haptic controls. And so this is that slider device that I showed you before, being used to segment a 3D volume. And I'm going to skip ahead because this is really just a very early prototype. We had much cooler versions of this later on. So this guy, Jim Smiley, joined our lab a couple of years ago, and he is a very good electronics wizard. And he saw our 3D physical axis, and he was like, well, what if we made them wireless? And we were very impressed by his technical capability, because he realized that concept quite quickly. So so this is the new improved version. Oops. Okay, this is the so-called MADE axis, modular actuated device embodying a data axis. So actuated because these sliders, they're not just passive sliders. They actually have little motors, and so they can give you haptic feedback as well, which is really nice. So they had Bluetooth and And we also added tracking markers so that we could position them in 3D with our Vicon system, and explored the design space, which was quite huge. And let me show you the result.
Axis, a modular actuated device to embody a data dimension into a physical axis. Our wireless handheld controller consists of 2 actuated sliders, a rotary encoder with switch, and an illuminated push button, allowing tangible, modular, and intuitive embodiment of an axis in traditional 2D desktop visualizations, as well as immersive visualizations in AR and VR. Multiple tracked made axes can be combined as collaborative building blocks. For example, in this case, a collaborative HoloLens application. Here, each made axis represents a single data dimension, and users can creatively build and control a range of visualizations using the IMAXIS visualization system. In this example workflow, we create a modular parallel coordinate plot using a vehicle dataset. We can see that increased horsepower correlates with faster acceleration to some extent, but clearly results in poor fuel efficiency. Adding the weight dimension and the number of cylinders then shows us that these are all extremely heavy 8-cylinder vehicles. Selecting 4-cylinder vehicles shows us the increase in fuel efficiency at the cost of acceleration and horsepower. An optically tracked made axis becomes a VR controller. Here, we instantiate or delete an axis with the rotary button press, and use the rotary control to select the instantiated data dimension. Our 2 sliders control the filtered minimum and maximum. The actuated sliders snap into place as each axis is selected. The top button allows for grabbing or arranged selection.
I'm going to skip ahead because this one goes on for quite a while. Okay. So there was we had a lot of fun with those made axes devices, as you can see, and there were a lot more nifty kind of interactions that we played around with. So I would refer you to the paper to check out the full design space that we explored there. But there was one fundamental problem with those devices, which is that they had to sit on a table. If you let go of it, it would obviously just fall to the floor. So we decided to see if we could use a robot to hold a made axis for us. That was literally the idea we had, and our student Xia Zhang did a fantastic job of realizing that idea, and I'll show you the result, which is a kind of encountered haptics system, where, as you can see here, the robot can position the slider directly where it needs to be to correspond with interaction elements in the environment. So here we're selecting just across a single axis. Okay, and here we are able to do our 3D image segmentation that we were doing earlier, but with just a single slider manipulated by the robot. So depending on where you reach out, the robot places the slider to allow you to slice according to any of the controls that you see in VR. So the VR view is on the left, and what's actually happening is on the right. And so the nice thing about this, obviously, is that you have a much larger interaction volume. The physical slider construction that we had at the start, they're just 10 centimeter sliders, whereas here we can go up to about 70 centimeter cube. Here's another kind of use case we developed. So this is so-called DIMViz system. So this is a time series data. And as you, and this was originally proposed by Kondo et al. On a touch screen system. And here we use the slider to interact with trajectory curves. So this is sort of pushing the idea to the limit, I think, where you're interacting with a nonlinear trajectory using this linear slider. So that was kind of cool. Okay, so I guess in summary, I've shown you a bunch of systems that we've had a lot of fun producing. Also some empirical study results that we had along the way. There's other results from the community that are starting to be quite exciting about. For example, this one here from a couple of years ago, Kraus et al. People in Konstanz found real benefits to 3D cluster perception in immersive environments. And I also want to take the opportunity to invite you all to Melbourne in October this year for the Viz conference when we host it here in Melbourne. We're deep in the throes of planning that at the moment, and we've got some exciting things on the agenda. So I do hope you'll come, and well, hopefully you've already submitted your papers, and I hope you'll come and present them in person later this year.